plugging away one by one at some of these known binary central stars, trying to get parameters for these things, and a number of collaborators up here, several of whom are here. So currently we know of about 45 close binary central stars. Close here meaning orbital period of about 13 days or lower. There are a couple with longer periods, but they're not understood quite as well. And by known, I mean that only about half of these so far have been confirmed spectroscopically as binaries. We think most of them are, if not all of them. It's difficult to describe the light curves that we see without that. And most of them have been discovered using photometry, using variables. This became much more complicated when Kepler came along. Kepler made a lot of people's lives more difficult, including ours. You can see Ursula's poster back there for more information. Only 12 of them have full binary models so far, and I'll explain partially why that is in a minute. And there are at least 3 more in progress. I think there are a few other people. Romano is working on 1 or 2 models as well. So we're getting to numbers that might actually be able to start saying something about these things. And in addition to those 12, there are a handful of others that have some identification of the companion star. So one of the reasons, or the reason there are only 12, is there are difficulties in modeling these things. The first difficulty is that only about 8 of them are bright enough that we can obtain spectra and radio velocities with 4-meter telescopes. The rest need 8-meter telescopes or larger. We tend to not get a lot of time for that. In addition to the observing time issues, nebular contamination is a problem, and Dave Jones mentioned this briefly yesterday. And by default, those 12 basically don't have the nebular contamination problem because they've been modeled. They either have a very faint nebulosity or the nebulosity can be subtracted out. It's smooth enough that we can get rid of it in photometry. The reason that causes a problem is it contributes third light, so the amplitude we see in the variability is smaller than the intrinsic variability. It makes it modeling difficult, especially when we're using multiple filters. So there are some binary central stars that probably never have decent models. One difficult one is NGC 6326 up here, and you can see the central star in there and why we might have some difficulty with the nebulosity. Ranges of parameters are fairly typical for central stars and main sequence stars, and you can see that for both when you throw in the central star and the companion, some of these parameters have ranges of 2 orders of magnitude, which makes the parameter space incredibly large when we're modeling these. There are lots of local minima, so we have to be able to constrain quite a few parameters before we can model them. And sometimes, in part because of that, some parameters are just ignored, which is not a good thing. But it happens occasionally, perhaps because some folks who are working on these don't realize that some of the parameters can be constrained, or they simply choose to ignore them because it makes the modeling more difficult and they're trying to come up with some kind of model. I've shown this particular distribution before the last APN meeting. This is an updated version of the orbital period distribution of the known central stars with main sequence companions, or the ones we think have main sequence companions. So this is more than the 16. This is from the total sample, and breaking it out, trying to get an average of what we believe the companions are like. And so the hatched region here is our sample of central stars. The green region are the Sloan Digital Sky Survey post-common little binaries. And at the last conference, they overlap pretty well. Here, with updates in both distributions, we can see that perhaps the Sloan sample goes to slightly smaller periods, which we might expect if there's some evolution towards smaller orbital periods or shorter orbital periods over time. One of the interesting things that's come out of this is the number of double degenerates we've discovered in these systems. If we see ellipsoidal variability in the light curve, it's almost certainly a double degenerate, simply because of the types of system we're looking at. Two visible eclipses means that it's likely a double degenerate, not always. And if we just take those two pieces and look at the sample, 25% of those that we've observed would be double degenerates. We can also find double degenerates by observing single line radial velocity variables where we can rule out a cool companion. So, if we look at that a little more closely, we realize that double degenerates are actually less likely to show photometric variability than main sequence companions. The reason for that is, as these stars evolve, it's the central star itself, the object that shed the planetary nebula, that is creating the variability. And as it shrinks, it moves away from the Roche lobe, so we're less likely to see ellipsoidal variability. That will go away. And as it shrinks, we're also less likely to see eclipses. So a very rough calculation shows that for a typical mass central star, 0.56, 0.58, so the mass is somewhere in there, we probably are only going to observe about 1/4 of the double degenerates as photometric variables. If we go to lower mass central stars, they evolve more slowly, and so we'll see a larger percentage. It can be up to about 50% for low mass objects. So in general, if we look at the number we've observed, the number we expect to have missed, then there may be just as many close binary central stars that have a white dwarf or subdwarf companion as have a main sequence companion. And in fact, if the binary fraction is around 15%, that fits in really nicely with the Supernova 1A progenitor survey, where they find that 15% of all white dwarfs are close double degenerate binaries. And that is, in fact, about a number of million. So that's a general overview of the sample we have right now. If we look at specific targets, we find that of the 16 with identified companions, 7 of them are M spectral type main sequence stars. 1 is a K star, 2 are G stars, those are all main sequence types, and 6 are white dwarfs or subdwarfs. 4 of those come from the expected photometric variability, ellipsoidal eclipses, and 2 were discovered in other ways. So those 2 are some examples of the ones that have evolved away from the Roche lobe and don't show eclipses. The main sequence companions with masses and radii is something that Dave Jones also alluded to yesterday. We see that for their mass, they're simply too large and too hot for main sequence stars. And this is pretty standard among post-common envelope binaries. It's generally seen. There are a couple of exceptions to that in the planetary nebula central star binaries. One is not too large and one is not too cool. Actually, I double-checked. I didn't change the temperatures there. There's one that fits with main sequence temperature. But we occasionally see post-common envelope binaries with that as well, so it's not out of the ordinary. If we look at the central stars then, rather than the companions, the range in masses go from about 0.51 to 1 solar mass. Some of those masses are assumed. So in the modeling, we have to narrow down the parameters, and sometimes, if we can't do so enough, we might say, well, we'll just assume that it's a typical mass for a central star and go on with the modeling and see if the modeling turns out to be consistent with that assumption. Of course, it doesn't mean the assumption is correct. That is not the case for most of the models, though, only a few of them. So the interesting thing that we see there is that none of these things are low mass central stars. None of them appear to come from post-RGB evolution, which is interesting. There are some models of common envelope interactions that predict that most of them will end up as post-RGB stars. Some predict that a smaller percentage, I think the smallest percentage I've seen is 15% or so. So the fact that we see none of them so far is interesting. And when we get some more numbers, it may tell us something more about the actual evolution that's going on. Central star temperatures and radii are in the ranges that we expect. But what we see from that is if we put it all together and we have nebular models that give us an age, then we find that the central stars that we model are consistent with the evolutionary models. If we look at binary parameters and relate those to morphology based on the companion type, that is the spectral type, whether it's a main sequence or compact companion, the orbital period, and the central star mass, right now we don't see any correlation at all with morphology. In other words, we don't see bipolars as the double degenerates and elliptical nebulae as main sequence stars. We don't see jets coming from a specific type. But we're just getting to the point here where we can start to think about this stuff. So stay tuned for that. And in fact, see Miguel's talk coming up. One correlation we do see, which you see also in Dave's talk, is a correlation, very strong correlation between binary inclination and nebular inclination. And there is a correlation in another respect. Riviera mentioned yesterday that we'd like to see spherical planetary nebulae in round studied. We're doing this. We're studying data for this 2 kiloparsec sample, have been for 5 years, and studying the spherical planetary nebulae looking for photometric variations is definitely a job for someone who has tenure, because it's dry and boring, because there's nothing there. We don't see any variability in the central stars of spherical planetary nebulae. That sample, the 2 kiloparsec sample, is about 75% completed at this point, and we're continuing that. So, major points. It looks right now like we may have just as many close binaries with the white dwarf or subdwarf companion as with the main sequence companion. We have no known post-RGB stars in the current sample of close binaries. Current central star parameters are consistent with evolutionary models, but it would be nice to get some more eclipsing variables in order to study that. And there are no known binary central stars in the spherical planetary nebulae.
Well, there are no binaries in spherical games already.
So I think you see two companions in very type where people typically associate that with close common, but there's at least one other way to know is to get very close companions without complete common books, which is if you have a tertiary. Yeah, so that may be somewhat consistent with avoiding RGB. Also, too, it may be consistent with your companions being hotter and healthier than you would otherwise be, because you have to damn the orbital energy in the companion, not the orbital.
Yeah, and I've been looking at Robin Chartreau and Carolina's sample for wider binaries that they observed, and trying to observe those to see if there are any tight binaries in there. There's one that's kind of suggested that there might be a close binary, but we haven't seen any with tertiary companions so far. Certainly doesn't mean they're not there. They're really hard to see.
Yeah, I mean, you can be pretty far away.
Yeah.
Nice talk. I have a question about the central stars and planetaries at peak luminosity. As Chardula has pointed out over and over again, we don't really understand the heat of the PNLF and why the heat is the same in early type galaxies with old stars as it is with young stars. Do you have any particular information about the nature of the central stars in the really luminous planetaries?
No, not yet. One of the statistics that we certainly need to look at, but it's literally just in the last 1 to 2 years that we've had a sample that's large enough to even start thinking about looking at some of those. But certainly something to know for us to look at.
Yeah, so the question for the table is about
Knowing by your high frequency of double degenerates, looking at precursors and those stars showing sort of variability, not one shows any symbiotic emission lines that you might expect from the white dwarf. So that would indicate less than 1%.
Yeah, that's why I asked my question to you yesterday, because it's really a fascinating dichotomy there. We need to figure out something. But a quick note, in our sample, the photometric sample of David's biggest 2 kiloparsec sample, we're finding binary fractions that are actually lower than Brent's from his paper, probably more like 10 to 13 or 14%, somewhere in that range. We're not done yet, but right now it's suggestive that what we're seeing is a lower percentage. Although we're missing some of the double degenerates, so if you add those in, it goes right back up to David's percentage, or to the Brent's percentage.
So just a question, why does the ellipsoidal variability indicate double degenerate?
Because if there's a main sequence companion there, the irradiation effect almost always swamps the ellipsoidal effect. The ellipsoidal effect is small in these systems, most at 10 to 2/10 of the magnitude, and the irradiation effect for stars that are that close together, especially if one of them still owns Roche lobe, would be huge. It would be at least 3 or 4 times the magnitude. So if it's dominated by ellipsoidal, it's almost always a double degenerate.
Yeah, more questions? Newton stars.
So, okay, let's move to the next speaker. European speaker? Speaker go into the book. I knew it. Okay. Miguel will tell us what Dave Jones wants.